All right, IB Physics. So in class, we set up our uh, free body diagrams for this roto ride, where our normal force is pushing towards the center of the circle, and so it's keeping the students in this ride. Then we also set up this loop-de-loop airplane ride, where the woman is upside down in this plane, and we considered all the possible different free body diagrams we could draw that represented the forces that would allow this woman to be going in this loop-de-loop. And again, remembering that the net force needs to point towards the center of the circle. So I thought you might find it helpful to have another problem that we go over, and look at this merry-go-round problem. And so we'll look at it right now and take some time to set it up. So if you don't need this video, you don't need to watch it. But if you're kind of stuck on this problem or you want a little review of how to set up a force web and then some free body diagrams, this is a great problem to listen to. So when I'm doing a force web, that means that I'm representing each different object in a situation and how they're interacting. So we have a boy standing on the edge of a merry-go-round. So we've got the boy, we've got the merry-go-round, and they don't have these at playgrounds very often anymore, but maybe you've seen one and you can spin it. So if you're on the ground, you push it and you can get it spinning, and when you're sitting on it, then you can experience circular motion and the forces associated with it. They don't have them anymore because people sued frequently when kids got injured on them. Kind of funny. So we've got the boy, we've got the merry-go-round, and then you want to think about what are the other objects that are important? Well, we're on Earth, so the Earth. Earth. I'm going to add that one in. So boy and the Earth, that's going to be gravity. And then you want to think, well, how is the boy interacting with the merry-go-round? Well, it looks like he is holding on to the merry-go-round. So I would say that means there's probably some force tension or normal force, but I'm going to go with tension. And let's see what else. So he's holding onto the merry-go-round. His feet are here on the floor of the merry-go-round, so the floor is supporting him upwards. And so the merry-go-round is also giving a force normal, pushing on his feet on him. So each of these lines represents a force pair where the boy pushes on the merry-go-round and the merry-go-round pushes back on him. And so we have our force web. Again, we're just focusing on the boy, so anything that's interacting with the boy counts. If it's not interacting with the boy, we don't have to worry about it. So notice that I don't have the ground or whoever might be pushing this merry-go-round. I don't have anything else because these are just the objects that the boy is interacting with. So then we go forward and we're going to draw two free body diagrams showing all relevant forces on him. And you might say, why do I have to draw two? And that's a fair point. But the reason that we're going to draw two is so we can get kind of two different perspectives. And so the first perspective is I'm going to draw an overhead view. So you could call this a bird's eye view. You could call it an overhead view. It's like we're looking down on the merry-go-round, and here's the boy and the little thing he's holding on to. And so overhead, we can't really see very much that's going on, but the boy is there. So overhead, we can see that the boy is holding on to the merry-go-round, and we can't see force gravity. So based on how I've drawn my overhead picture, actually, let me draw my overhead picture slightly differently. So here's the merry-go-round. I'm going to put the boy right here. So this orange dot here, that's going to be where the boy is. So the boy is holding on to the merry-go-round with force tension. And I actually know that the boy is holding on to the merry-go-round, and the force tension of the boy's arm holding onto the merry-go-round is pulling him inwards towards the center of the circle. This could alternatively be like force normal, And again, this is an overhead view. So I can't see force gravity and I can't see force normal because those are in the up-down area. So then I'm going to do a sideways view. Sideways. And again, I'm going to try to draw a little picture. So in the sideways view, you can't see the circle of the merry-go-round. But here's the merry-go-round. It's like stuck on something, and there's the ground. And the boy is here holding on to the little merry-go-round things. So that's his arm holding onto the merry-go-round thing. So in my sideways view, I can represent all of the forces actually, which is pretty nice. I can have a force gravity downwards. I can have this force normal upwards. I know that these two are going to be congruent because I know that the boy is not going to fall through the merry-go-round. And then I've got my force tension here towards the center of the circle. So I've got these nice free body diagrams. And interestingly, okay, so we've got these nice free body diagrams, and I got us a picture of them. I feel very smart. And so we're going to go ahead and move forward into part C, where we're going to use Newton's second law and our forces table to indicate the resulting accelerations in 3 directions. OMG. So the 3 directions that they have here, I want to kind of outline what they mean so you can get a really good sense of what these words are actually telling you about. So we have one direction that says radial. And what radial means is that it's along the radius. Maybe I should do a different color. Let's do red for radial. It's along the radius of the circle. This would be radial in that picture. And radial in this picture, again, is going to be along the radius of the circle. And so this is where having 2 different versions of my free body diagrams comes in really handy. So our radial direction, I might call the x direction, just because that, like, you know, it's the horizontal, and we're going to call that radial in this case. So in the horizontal direction, I want to know what are the sum of the forces in the x direction. Well, it looks like there's force tension. And that's it. That's the only force that's in the radial direction. It points along the radius of the circle. So we've done radial, go team. Then we want to do tangential. And tangential is a little bit maybe challenging to think about. So tangential, and have this be green. That means tangent to the circle. So tangent to the circle is going to be right here. This is tangential. So, and I'm going to call this the z-plane. There's a reason for that. And we're calling it tangential. So it's tangent to the circle. And if I look at that in the other picture, well, that would be like a little arrow going right here. Like that's the line going into the page or into your iPad. It's perpendicular to right here. We can't even really see that direction in this picture. And so my tangential direction actually has no forces in it. No forces. So that's why I called it the z direction, because we don't use z very often, so no forces make sense. Then our last direction is perpendicular to the plane of the circle. And so what perpendicular to the plane of the circle means that it's like coming out of the circle. It's at a right angle to the plane of the circle. So in our sideways view, that's this way, and that would be perpendicular to plane. And so that direction, I'm actually going to call the y direction. And in this picture, that would be like a dot going into the page. You can't actually see that axis in the overhead view because overhead is looking downwards on it. So that's going to be the sum of the forces in the y direction, perpendicular And here we have two different forces, and we know that those forces are the force normal from the seat, the chair, or not chair, like floor of the merry-go-round. And then I have force gravity. That's going to be downwards. And those are going to add up to 0 newtons, which results in 0 acceleration. And then in our radial direction, that's where our forces are going to add up to be our net force, F net, which will equal the mass of the boy times the acceleration of the boy. And so when we want to think about what combination of forces are providing the circular motion, well, those are the forces that are providing that net force. So the net force in this situation, the net force is from the tension in the boy's arm holding onto the merry-go-round. So the boy's arm is holding on with tension to the merry-go-round, and it's pulling him in towards the center of the circle. Whew, got a lot going on. So hopefully this was helpful for you in understanding what these different directions mean and setting up our free body diagrams for our circular motion situation. We'll keep working on these in class next week, and we'll be adding in numbers so that we could say, hey, if the merry-go-round is going this fast, what does that mean the force on the boy needs to be? Thanks, folks, and good luck.